All right. So today we're going to work on section 2, which is limits involving infinity. And to infinity and beyond is our cutesy title, but limits involving infinity. So let's start by considering the limit as x approaches positive infinity and also the limit as x approaches negative infinity. And we'll start by graphing y equals 1 over x. This is an interesting function that you've seen before. Remember, there's two branches in quadrant 1 and in quadrant 2. And there's a horizontal asymptote at along the x-axis. Yes, because as y equals 0 is a horizontal asymptote because, and this is technically y, because the limit as x goes to positive infinity of 1 over x is 0, and also the limit of 1 over x as x goes to negative infinity is also 0. So remember that limits are your y values, and so as x is getting larger and larger and larger, you're going along that line, your y value is approaching 0, and then also as x is getting smaller in the negative direction, well, you're going to negative infinity, so it's getting large, but in the negative direction, your y value is also approaching 0. So by the definition of a horizontal asymptote is the line y equals b is a horizontal asymptote of your function f if the limit of f of x as x approaches infinity is b, or if the limit of f of x is as x approaches negative infinity is also b. So let's look at the function 2 plus 1 over x. If you remember your transformations, you're taking the parent function of 1 over x, which is that graph there, and adding 2 to it. So we're going to take this whole thing and we're shifting it vertical shift. Do you remember transformations from last year? Take that graph, shift it up 2 units, and so now my horizontal asymptote is at y equals 2. And so y equals 2 is a horizontal asymptote because, so the same reasoning, right, that since the limit of, it doesn't matter if x is going to positive or negative infinity, the limit as it's going there, the y values are approaching 2. So as x is approaching positive infinity, you're going in this direction, your y values are getting closer and closer to 2. And as x is approaching negative infinity, your y values are also going to 2. All right, let's look at this function, x divided by the square root of x squared plus 1. Let's put that in your graphing calculator and put it under y equals and then x divided by square root of x squared plus 1. So here's the graph that you should have gotten on your graphing calculator. And to look at even better, which I don't have a picture on here, but if you were to go to table, which is, you hit second and then graph, you'll see in blue writing above the button graph, you'll see table. If you were to do that, you could put in a bunch of values that are getting larger and larger. So if we want to look at the limit of this function of x over square root of x squared plus 1, as x goes to positive infinity, as x is going to positive infinity, if you look at the table, it's even more obvious, right? That if you put in 5 and then 10 and then 20 and then 100 and then 1,000, 10,000, right? You'll see that the numbers are getting closer and closer to 1. Also, as the limit goes to negative infinity, you are going to be getting closer. Your y values are getting closer and closer to negative 1. So notice that the right side limit, like not always, you can't always say as x goes to positive or negative infinity, because here's an example of the right-hand side is going to positive 1, and the left-hand side, the y values are getting closer to negative 1. So it's okay that the left and right-hand sides were different. In fact, very rare for a function to have the same thing happening on both as it's going right or left. It happens, but it's more common that they're not doing the same thing. We talked a little bit about the squeeze theorem or sandwich theorem. not that you have to really know that super well yet, but it does work using positive or negative infinity. So f of x equals sine of x over x is a very popular one. You're going to want to know what happens to this function. AP College Board likes this function. So the limit as x approaches 0 is actually 1. To confirm it, I highly recommend that you put that function sine of x divided by x in your graphing calculator, and you'll see that, you know, as x is going to 0, your y value is looking like 1, even though really you've got a 0 over 0, right? And you'll find out in, it's a while, I want to say it's second semester, chapter 9, you'll find L'Hopital's, you'll find out about L'Hopital's rule and see why it is the way it is. But looking at a graph, you can see that the limit is 1, even though technically, you know, sine of 0 is 0 and divided by 0. So really you've got a 0 over 0, which means nothing to us at this point. But in this case, it is actually equal to 1. And then the whole sandwich theorem and squeeze theorem works using positive or negative infinity. And that is because we know sine of x is bounded between positive 1 and negative 1. And then if we divide it by x, then that means that sine of x over x is actually bounded by negative 1 over x and positive 1 over x. And then we know what happens to 1 over x as it's going to infinity. They're both 0, which means that this guy has to be 0 also. If that's confusing to you, we can go over that more in depth in class. And then the properties of limits as x goes to infinity are the same as when x goes to positive or negative 1. So the sum of two limits, the difference of two limits, the product, the quotient, constant multiple, and the power, they all work for limits as x is going to positive and negative infinity, just like they do when x is going to positive or negative. C means a constant. So, but the rules, those properties of limits work for when we're looking at positive or negative infinity as well. All right, so let's look again at this graph of y equals 1 over x. And again, two branches, positive axis, positive quadrant 1, and then quadrant 3, right? These two branches. If you remember, these are hyperbolas, but just on with a little twist. That's throwing it out there, huh? All right, so now let's look, instead of looking at the vertical or the horizontal asymptote, let's talk about the vertical asymptote, because do you see also that these graphs are coming up really, really close, but not touching. Really, really close, but not touching that asymptote. So we have a vertical asymptote at x equals 0. That's that vertical line there. And so the definition of a vertical asymptote is the line x equals a meaning just some constant, is a vertical asymptote of f of x if either the limit as you're approaching a from the right is positive or negative infinity, or the limit as your x is approaching a from the left is positive or negative infinity. Sometimes they'll both go up, sometimes they'll both go down. In this case, one is going up and one is going down. It just depends on the function. So frequently there is a vertical asymptote whenever we have the denominator equal to 0. So in this case, 1 over x at x equals 0, you've got a denominator of 0, you know, dividing by 0 makes it undefined, right? But not always, not always. Sometimes, most of the time when you're dividing by 0, you'll get a vertical asymptote. But sometimes, do you remember there was a removable discontinuity sometimes, or even, remember, sine of x over x, this is that function that I said to you College Board really likes. You definitely need to know that the limit as x goes to 0 of this guy is 1, which by the time that you end up taking the AP exam, this will make sense because you'll know L'Hopital's rule. And so when in doubt, you'll just, instead of memorizing this, you'll know you can do L'Hopital's rule and figure out that it is 1. But right now, look at a graphing calculator, right? Put that function in and look to see what happens when x is approaching 0. You'll see the y value is 1, whether you're coming from the left or from the right. So again, not positive or negative infinity, right? So where most of the time when you're dividing by 0, you get that vertical asymptote, but in this case, it's not. It's actually equal to 1. Okay. Let's talk about some end behavior models. Yeah, so be careful on that. Don't just assume that since you're dividing by 0 that it's equal to, that it's a vertical asymptote, because that doesn't always happen. All right, I want you to put in your graphing calculator under y1. I want you to put in 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6. And then under y2 in your graphing calculator, put in 3x to the 4th. And then change the window. So after you put those in, you'll hit window. And this notation just means x min, x max. And I would leave the scale as 1. And then y min, -5, y max 20. That's 25. I think I left them as just y scale of 1, but if you don't like a whole bunch of tick marks, you could make that a little bit bigger. It doesn't matter. And then, so I want you to do that and look at those two graphs of 3x to the 4th minus blah, 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 versus y2 is only 3x to the 4th, right? It's got the same leading term. Hopefully you notice that, 3x to the 4th, 3x to the 4th. It's just this one has a whole bunch of other junk added after it, right? Which is a lot more common when we're looking at polynomials. So I want you to look at that, and you can see, here's what the graph should look like, yeah? You've got, here's just this one right here would be the y2, the 3x to the 4th, versus the one that's kind of wonky doodle, has all of these other numbers after it. So that's in this original window. Then what I want you to do is go back to window and change x min to -20, x max to +20, y min, and then do we change? I might change the x scale, because that would be 40 little dashes. So maybe the x scale, make it 5 or something like that, or 10. It really doesn't matter. You could even make it 20, make it 100, doesn't matter. The x scale just tells you how often a tick mark should show up. And then y min, put negative, what is that? -100,000. And then y max, do 500,000. And I would definitely change the y scale there. Either that, or maybe it just makes the y-axis super dark. But I would change it. I'd probably do it like every 10,000, maybe something like that. Make the y scale 10,000, or even 100,000. Anyway, but here's the point. Yes. Here's what it looks like when you change the window to this. So what we did by changing this window is, imagine this graph is if you look at it from the top of a building. Say it's on the ground and you're looking at it from the top of a building, versus these are what the graphs look like if you're up in an airplane looking down, or if you're up in space and looking down on it. And do you notice that as we zoomed way out, we made this window be super large, and we're up in space looking down, they look the same, right? But we know zoomed in, they're not the same. But as you zoom out, they look, I mean, they are just right on top of each other. And so that brings us to the whole end behavior model. Remember, I pointed out this guy started within 3x to the 4th. So did this guy is only 3x to the 4th. And as you zoom way out, they have the same end behavior. Yes, as you zoom out, they are the same thing. So zooming out meaning, so like as I'm approaching x, as x is approaching positive infinity, they basically take on the same amount. And as x is approaching negative infinity, your y values end up being basically the same as you're approaching positive and negative infinity. So I'm going to show it to you mathematically wise. Yes. I'm going to take a limit as x goes to either positive or negative infinity. We're going to be lazy and not write it twice, of f of x over g of x. So replace f of x with this whole big old long polynomial. Boom. You do, by the way, you do have to keep writing the limit as x approaches before each of the functions, because otherwise it's gibberish. Yes, you must have your limit notation there. So the limit as x approaches positive or negative infinity of up top is f of x, bottom is g of x. And what we're going to do now is actually simplify this thing. You know, you've got to a monomial in the bottom. So I'm going to write it as 3x to the fourth over 3x to the fourth. Don't want to show that yet. Okay, so I'm going to split it up. I'm going to go 3x to the fourth over 3x to the fourth. That would just be 1. Put negative 2x cubed over 3x to the fourth, right? Separate that fraction. You'd be left with a negative 2. This x cubed would cancel. You'd be left with an x in the bottom and the 3 in the bottom. When you split these guys up, 3 over 3, you just have a 1. X squared over x to the fourth, you've still got an x to the squared down in the denominator. And then negative 5x over 3x to the fourth. You'll have a negative 5 over 3x cubed. And then 6 over 3x to the fourth would leave you with a 2 over x to the fourth. So I split it up. Yeah, split up each of these fractions. And this is why I do it. You ready? Now I'm going to take, remember the limit properties hold for plus or minus infinity. So when I take the limit of each of these pieces, yes, so the limit as x approaches positive or negative infinity of 1, well, there's nothing to plug into x, so that's just 1. But 2 over 3x, that's like 2 over infinity, so that zeroes out. 1 over x squared, it's like 1 over infinity, zeros. 5 over 3x cubed, you got an infinity down the bottom. And then 2 over x to the fourth. So anytime you've got an infinity in the bottom, we say the limit, it's going to go to 0. Yeah, anything with an x down in the denominator, it's going to go to 0 if there's a constant up top. Yeah, they just go to 0 even faster than 1 over x. All right, so taking the limit as x goes to plus or minus infinity of 1 minus 0, 0, 0, 0. So it's just 1. Well, isn't that nice? Okay, so this is going to come in handy because what that tells us is 3x to the fourth, because that's what was down in the denominator, is going to be our end behavior model. It matches up with this graph that as we zoomed way out, as we go to positive infinity or negative infinity, they basically look the same. The end behavior model is just the 3x to the fourth. It's not 3x to the fourth and 2x cubed and blah, blah, blah. So 3x to the fourth is the end behavior model for this big old long function here. So let me give you the definition. A function g of x is a right end behavior model if and only if the limit as x approaches positive infinity of f of x over g of x is 1. So g of x is a right end behavior model of f of x if as you're going to positive infinity, yeah, it's equal to 1. So right end, if you're taking it as x goes to positive infinity, think about it at positive x's, right? So positive x's are to the right. So if you're going to positive x's, then it's a right end behavior model. And then g of x, so same thing, f of x divided by g of x, but this time we're going to go to the negative infinity, right? So we're going to negative numbers, we're going to the left. So it's a left end behavior model if as x is going way, way to the left and you divide these two and you get a 1. So both of these end up equaling 1 as you're taking the limit as x goes to positive or negative infinity. The difference is it's the right end behavior model if you're going to the positive x values, and it's a left end behavior model if you're going to the negative infinity. All right, so we can have a different right end behavior or a left end behavior. We're going to do an example with that. But if the right equals the left, like the last example, right? The last example, if we took it as positive or negative infinity, they both ended up being 1, then we just call it the end behavior model. So notice that on that last example, both, whether you're going positive or negative infinity, they both matched up, yes? And so we say left, we just call it an end behavior model. So let's do this one. I'm going to show you the shortcut now, because who wants to show all that work, right? Do you want to know the shortcut? Of course you want to know the shortcut. When it's a polynomial over another polynomial, right? All you've got is x to the power and x to the power. All you have to do is look at the leading coefficient. Well, the leading term, I should say. So look at on the top, the variable with the highest exponent is 2x to the fifth. That's the term that has the highest exponent. See how it's got x to the fifth, x to the fourth, x squared, 1. Okay, 2x to the fifth is the largest. exponent of all of these terms on top. So the top, you got 2x to the fifth. On the bottom, look the same thing, because they're not always in order, right? In this case, they are in descending order, but sometimes they don't have to be. So out of the terms in the bottom, in the denominator, 3x squared is the largest exponent. On the bottom, you got that. All right, so you get to ignore all the rest of this nonsense, right? Because as we're going to infinity, like you saw on that previous example, on example 4, you saw that as we went to infinity, it just ended up being the leading coefficients, right? So when we divide this, simplify it, 2 and the 3 will stay, but x to the fifth and 3x squared, you can simplify that. That would leave you with an x cubed on top. There is your end behavior model, the end behavior model on this guy. And that'll work anytime. It's a polynomial over a polynomial. Look at the highest power on top, highest power on the bottom. Consider those your leading coefficients. Put them on top of each other, simplify, and there's your end behavior model. So if the coefficients had matched, like let's say this had been a 2x squared, then the 2's would have canceled and it would have just been x cubed would be your end behavior model. So you always keep the coefficient that's in front of that leading term. Okay, so here is one polynomial over polynomial. You're just going to have an end behavior model. Oh, I take that back. No, I do. No, that's right. Yes. Polynomial over polynomial. Because what will happen is as you go to negative infinity, that'll be negative, and then positive infinity will be positive. So yeah, that is just this. It will totally, if you put this whole thing as your f of x, and then you put this under y2, so put this guy as y1, this guy is y2, and then zoom way out, you'll see they'll overlap just like that other example did. Okay, now, not always do the right and left ends match. So let's look at an example with that. They might be different. You know, the right, as you're going to positive infinity, it might behave one way. And as you go to negative infinity, it might be another. And so here's an example. How about the function x plus e to the negative x? Yeah, so this isn't a polynomial over a polynomial. You got to look at it. But what you're going to do is look at each of these functions separately. Look at y equals x and look at y equals e to the negative x. And what you want to think about is who's more powerful or who's the boss when you're going to positive infinity, and then who's the boss when you're going to negative infinity. So I did put in both of these functions into Desmos so that I could show you a visual of what's happening. Because do you remember what the graph of y equals x looks like? I hope so. It's just a straight line, right? And do you remember what y equals e to the negative x looks like? It's going to be the decay model, right? It's the exponential, but decay. So here, I'll bring it up right now. There you go. Here they are. The red one is y equals x, and the blue one is y equals e to the negative x. All right, so let's look at the right-hand side first. Yes, and this is what I want you to think about is think about who's more powerful, who's the boss. As I'm going to positive infinity, you know, and we're adding these guys together, right? So, you know, adding these two y values together, adding these two y values together. Do you remember doing that last year? Adding the two y values together. Well, do you see that e to the negative x, your y values are going closer and closer to 0, but the x, y equals x, is getting larger very steadily, very slowly, right? You know, when x is 5, y is 5, and when x is 10, y is 10. But here's the deal. E to the negative x as when x is 5, well, you've got e to the negative fifth power. That's 1 over e to the fifth. Yeah, it's small. It's like almost 0, right? So basically, when you're adding these two guys together, this red graph is way more powerful as you're going to the right, because you're basically adding an almost 0 to each of these values. So definitely, as you're going to the right, so as x goes to positive infinity, y equals x is a way more powerful function. It's overpowering the e to the negative x. Okay. So that means I'm going to claim that y equals x is my right end behavior model. And I believe I show you worked out also, like how to show it. algebraically or analytically, right? So this isn't a proof just looking at the graph, but I'm going to show it to you in writing. All right, now let's look at to the left. For the left-end behavior model, I'm looking as x goes to negative infinity. And hopefully you can see that, so the y equals x1, all right, you're going to negative infinity. On the graph of y equals e to the negative x, I'm going to positive infinity. But do you see that even at, let's look at when x is 2, negative 2, all right, your y equals x graph is negative 2, but your e to the negative x is e squared. That's like almost 9, right? Well, not quite, but yeah. All right, so it's bigger. And then when you're at negative 5, I can still see the y equals x graph here, but I'm already off the graph. When x is negative 5, well, then I've got an e to the 5th, which is about somewhere between 32 and 80, no, 3 to the 5th would be what? 243, I don't know. But so somewhere, it's large, right? It's definitely bigger than 32. Because e is about 2.7, blah, blah, blah. So that's why I'm saying it's between 2 and 3. 2 to the 5th would be 32. Now I'm questioning myself. Hopefully that's right. That'd be embarrassing if I'm telling you something wrong, but whatever. Right? 2 to the 5th. Hold on. Just have to confirm it for myself. 32. Okay. Yeah. And then 3 to the 5th, like 243, I believe. But anyway, so even at negative 5, your y equals x is only negative 5, whoops, sorry, versus e to the negative x is already this very, very large number, at bigger than 32. And when you get to negative 10, your at y equals x would just be negative 10, but e to the negative x would be zoom, way big. And then we're talking about going all the way to negative infinity, not just negative 10, negative infinity. So obviously the e to the negative x is way more powerful than just x. Hopefully that makes sense. All right, so I'm going to show you how to do this analytically, is what it's called when you're working it all out. So I claimed that x is my right end behavior model. And so let me prove it to you. Remember that to show that it's the right end behavior model, you're going to take the limit as x goes to positive infinity. My f of x is the whole thing, x plus e to the negative x. And then I'm going to divide it by, I'm claiming that x is my right end behavior model. So I'm going to divide it by x. And when you simplify this, you'd have x over x would give you 1 plus e to the negative x over x. Well, as you're going to infinity, e to the negative infinity gets shoved down in the bottom. Does that make sense? Do you remember that negative exponents? It's the same as I could move this, make it a positive exponent and put it down in the denominator as an e to the positive x. So now I've got a 1 over x times e to the positive x, and I'm going to x is infinity. You're definitely dividing by infinity. And so this guy zeroes out, and you're left with taking the limit of 1 plus 0. And so that's a 1. That's what I needed to show. That's what you're going to have to do on the test, is show this work of, okay, it takes it to 1. That makes, that has confirmed the fact that my gut reaction by looking at the graph was x is my right end behavior model. I just confirmed it because I got a 1 as I was taking the limit as x goes to positive infinity. Now my claim was also that e to the negative x is the left end behavior model. So on the left, remember when we're showing left, I'm going to take the limit as x goes to negative infinity. And I wrote it as f of x over h of x this time because it's a different function. And I'm claiming now my h of x is going to be e to the negative x. So f of x is the whole thing. So I write the limit as x goes to negative infinity of x plus e to the negative x over e to the negative x. And splitting it up, x over e to the negative x, and e to the negative x over e to the negative x, which that's just a 1. Okay, so let's come over here. When you're not truly plugging in a negative infinity, but hopefully you can see that when you're when you're putting in a negative infinity into this x, it actually becomes e to the positive infinity. So that's a huge infinity over another infinity. Anyway, this ends up zeroing out because this guy is way huge. And so it ends up zeroing out and you just end up with a 1. All right, we can also investigate difficult limits using reciprocals. So the limit as x goes to positive or negative infinity of just f of x is the same as if you were to take the limit as x goes to 0 of f of 1 over x. Yeah. So notice this is the reciprocal. So think of the reciprocal of infinity. 1 over infinity will give you 0. And 1 over 0 will give you infinity. So we can do that as long as we're talking about the reciprocals inside these parentheses too. Reciprocal of x is 1 over x. So sometimes looking at one way, you're like, I'm not sure. But if we take the reciprocal, then it's easier. So let's look at an example with that. The limit as x goes to infinity of sine of 1 over x. You're like, oh, right? I don't know. But here's what we can do. We can rewrite this as instead of 1 over x, I can change it to x as long as I change this limit to, instead of it going to infinity, I'm going to change it to go as x goes to 0. So I changed the x going to infinity to x going to 0. I can do that as long as I'm taking the reciprocal of 1 over x, which turns it into x. All right, so when you plug a 0 into x, what's sine of 0? 0. So that is your answer. It turns out that the limit of sine of 1 over x as x goes to infinity is also 0. Okay, which isn't like, if I believe if you put that in your graphing calculator, it's not as obvious because it's still going to, be oscillating a little bit, if that makes sense to you, as you're going to positive infinity, but it's getting closer and closer to the y-axis as it goes. All right, so here is your homework. I do like my means. If you didn't have me for pre-calc, I do like my means. All right, so that was section 2. You all have a fabulous day.